Hello all. So, this is our next lecture in which we are going to have a discussion on CMOS logic propagation delay. Okay. We will discuss this one by one. So, basically CMOS that is stand for complementary metal oxide semiconductor, that is inside your integrated circuit. The most of the that transistor are fabricated by using of this CMOS technology. So, almost 90% of integrated circuit fabricated today that uses this CMOS technology. So, why we are choosing this CMOS for fabricating any integrated circuit? So, that we have to see, and as we know the CMOS has outperformed the BJT due to their following superior performance. Like CMOS exhibits, these are the properties. One, it exhibit very low power. Okay, that means the power dissipation of the CMOS circuit is very low. Second, in terms of area, if you see the BJT takes a higher area as compared to your CMOS. So, the low area due to less device requirement. Okay. The next is it is easily scalable. The CMOS can be easily scalable. So, as we know, we are going for a different technology node year by year. Currently, we are using a 5 nanometer technology node. So, having a CMOS in the circuit can be done with the help of scaling. Apart from that, the fabrication of this CMOS in the integrated circuit is very low. So, high production is achievable with the low fabrication cost. Now, if we talk about the design of this logic, that we can say the digital logic circuit is designed with CMOS transistor, which are most popular because of its low power dissipation, and you can say that requires a less area as compared to other logic circuits. So, the CMOS, you can see in the circuit, it is a combination of NMOS and PMOS logic, clear, where the NMOS and PMOS transistors are both functionally and structurally complement to each other, means NMOS is different and PMOS is different. So, in NMOS you are having electron mobility is higher, whereas in PMOS you are having hole mobility is higher. So, this combination of NMOS and PMOS is known as complementary metal oxide semiconductor, or you can say CMOS. Now, for a CMOS logic device, we will first see the inverter, clear. So, this is your CMOS inverter. So, we will see how it works. Okay. So, in general, as we know that if we are having this symbol of CMOS inverter, and if we are giving 1 as a input, the output will be 0, clear, that we know. If we are giving input as a 0, the output will be 1. So, it is a complement, clear. So, we will see how this truth table we are achieving, clear. So, A is our input, this is A my input, and this is Y, this is output. In this we will see what will happen when we are applying a 0 input to a transistor, okay, whether NMOS is on, whether PMOS is on, that we will see. So, when we are having input as a 0, at that time the NMOS will be in off condition, clear, the NMOS will be in off condition. That is why you can see that this is switch is open, this switch is open, and this PMOS will have a very small resistance. This PMOS is exhibit a small resistance. With the help of this small resistance, the VDD, the current will flow from this resistor and it will charge the capacitive load, clear, until unless we are having a supply and we are having 0 input as a 0 as a input, okay, the logic 0. That means the capacitor will slowly charge it and will charge fully. over the time, right. Now, once we are this input voltage change from 0 to 1, this capacitor will try to discharge through this ground. Okay. That means, when we are having input as a logic high, at that time my PMOS will be in off condition, okay, and this NMOS will have a small resistance, clear, that is internal resistance you can say. So, whatever the charge you have in the capacitor, it will slowly discharge, and the output you will see at the first you are having high input output, then slowly it will decay. So, this is my output for the input, this is 0, this is 1, 0, 1, clear. This kind of thing you can observe. Similarly, by using the CMOS, you can also implement 2 input NAND gate, you can also implement 3 input NAND gate, means k input NAND gate or NOR gate also you can implement. So, here you can see we are having 2 PMOS that are connected in parallel to each other and 2 NMOS that is connected in series, clear. In this you can see we are having 2 input A and B. So, if you see the output y in terms of Boolean expression, you will see A dot B whole bar, clear, and this is the logic symbol, this is the logic symbol of your NAND gate y A B, clear. So, if either of the input, so how the output you can observe, if either of A or B is 0, clear, at that time at least one of the NMOS will be in the off condition. So, suppose if any one of the NMOS is in off condition, that means there will be no current flow here. Okay. In this case, if this PMOS will be turned on, and once this PMOS is turned on, we are having here VDD, clear. So, the current will flow and we will have a high output as a logic 1, clear. Now, other than that, clear, when both the input A and B, when both the input is in logic high, then both NMOS will get on. When both A and B is in logic 1, then only this and this both NMOS will be in on condition and both PMOS will be in off condition. In that the output will be at logic 0, clear. So, this is how you can see the working of your 2 input CMOS NAND gate. Similarly, you can also design more number of inputs. So, k input NAND gates are constructed using k series NMOS transistor and k parallel PMOS transistor, clear. So, if you want a 3 input, then A, B, C, you have to take one more NMOS, you have to put it here and you have to connect it in the series, and one more PMOS you have to connect in the parallel, right. Now, we will see what this inverter and NAND gates, these two are the example of static CMOS logic gates, and sometimes it is also called a complementary CMOS gates. Okay. So, in general this static CMOS gate has an NMOS that is in pull down. So, this one is called pull down network. Okay. So, in this pull down network we are having a different number of NMOS either in the parallel or either in the series based on what logic you are design. Okay. Clear. So, if you are designing NAND gate, then this NMOS should be in the series. If you are designing NOR gate, then this NMOS should be in parallel. Clear. Similarly, we are also having a pull up network, means it pulling up the high level, that is why it is called pull up network, and this one is pull down network. So, in the NAND gate case we use a series pull down network and a parallel pull up network, that just I have shown in the previous slides. So, 2 or more transistors in series are on, and only if all of the series transistor are on, clear, and the 2 or more transistor in parallel are on if any of the parallel transistor are on, clear. In the previous slide that we have shown, if in this pull up network we are having PMOS, if any of the PMOS is on, that means you will have a proper current. But in the NMOS, I am talking about the NAND gate, if we are having a series, if any of the NMOS is off, that means you will not get the output, clear. So, these are the possible configuration that I have shown here. So, we can understand here how the series and parallel combination works for NMOS and the PMOS. Okay. So, first we will talk about this A and this B, because both are in series combination. Okay. But this one is NMOS and this one I am having PMOS, clear. So, this G1 and G2 is my input, you can say, clear. So, in terms of switching we can say, when both are off, means when we are applying a 0 logic at the input, then both the NMOS is in switch off condition, okay, and the overall output you will get as a off, means 0 logic, clear. Now, the second case, when any one is in off condition and the other one is in on condition, okay, the second input is in on condition, but the overall output you will have off only, because it is connected in series, NMOS is connected in series. Now, the third case, when the first one is your on and the second one is your off, we are having logic 1 and logic 0, you can say. At that time also you will have overall output as a 0, because there is a discontinuity of the connection, you can say. In the last, when we are having both input as a on, at that time both NMOS and PMOS both will work, okay, it will be on switch on condition and you will have the output, clear. Just opposite case you can take. In case of PMOS, when the PMOS is in series, when both are in 0, because PMOS will work when we are having input as a 0. When both are 0, then both will be switched on condition and you will have a proper output. Similarly, in the next one, if any of the input is high, then PMOS will not work and you will get off, you will get 0 logic, clear. In the third, again same case, you will have off. In the fourth, if even if you have both the input as a 1 1 1, the PMOS will not give any output, it will give a 0 output, okay. No output means 0. Now, in case of parallel, again this one is for NMOS and this one is for PMOS, right. So, in that one you can see that from A to B we have to observe, okay. So, both input is 0, if both 0, that means NMOS will have switch off condition and no output, means off. Second, if any one is on, that means there will be a flow of this current. So, from A to B you will have one path. So, this path will give on. So, it is having logic 1. Again in the opposite case, from here you will have on condition. In the fourth we are having both on, clear. So, these are the configuration that you can see. This is the connection and behavior of series and parallel transistors, clear. Apart from that, we are also having a pass transistor, okay. So, this also we can understand how this pass transistor behave, right. The strength of signal. So, by using this pass transistor, the strength of signal is measured by how closely it approximate an ideal voltage source, clear. That means, suppose if I am having a 1, that means 1 is VDD, you can say. So, your output strength is how much close to this 1, whether it is close to 0. If it is very much close to 1, then we can say it is having output as a 1. If it is very much close to 0, then we can say it is going for the 0, clear. So, the power supplies or rails, either VDD or ground, are the source of a strong 1 or a strong 0. By using pass transistor, you will have a strong 1 or a strong 0 outcome. Clear? Now, the NMOS transistor, we will see both NMOS and PMOS. Okay. So, we will see which one is giving a strong one and which one is giving weak one, that also we will see here. In the NMOS, you can see we are having a gate, G is gate, S is source and D is drain. Okay. So, I have taken both the cases, if the input is 0, if the input is 1. Okay. So, you can see when we are having a 0 case, at that time this switch is off condition. Okay. So, in that you can see this switch off or condition, and when this source is 0, okay, when the source is 0 and this G is equal to 1, means this we are having some connection here, at that time the output is also 0. So, we can say it passes a degraded or weak one, clear, that we can see. Similarly, when we are having a G is equal to 1, at that time the switch is on the on condition, okay, and we can also see from the input and output terms this one is degraded, clear. Similarly, you can understand for the PMOS, where we are having a source, gate and the drain, clear. Again the same switching phenomena you can see for the PMOS condition. In the NMOS condition, when you are having G equal to 0, the switch is off, but in the case of PMOS, when G is equal to 0, you are having switch in the on condition, clear. So, here you can see you are having a 0 and it will give you a degraded 0, means the magnitude of the toward the 0. So, it passes a degraded weak 0. Okay. So, this condition is also same as the previous one that I have shown, clear. So, you can see that this kind will have a weak 1 and this one is have a weak 0, clear. The similar phenomena you can also see in the transmission gate, which is which can be designed by combining NMOS and PMOS transistor in parallel to each other. So, from here you can see, if I will split this one will become the PMOS, and if I will split this one, it will be NMOS. So, parallel combination of PMOS and NMOS can be treated as a transmission gate. So, we obtain a switch that turns on when a logic 1 is applied to G, in which zeros and ones are both passed in an acceptable fashion, clear. So, this is also called a transmission gate or pass gate. In a circuit which only a 0 or 1 has to be passed, the appropriate transistor N or P can be deleted, okay. So, reverting to a single NMOS or PMOS device, clear. So, this logic function is similar as we have seen in the previous one. So, you can see this is a B and we are having G and complement of G, that is denoted as GB, clear. So, you can see when we are having G as a input 0 and GB is just opposite of your G, okay. So, we are having switch as off condition, clear. In that, when we are having G is equal to 1, then GB will be in opposite, okay. This one we are having 0, that means this switch will have in the on condition, and this is the actual symbol of your transmission gate, clear. And you can observe the input and output phenomena from here, which shows a strong 0 and strong 1 for the applied input. Now, apart from that, we have to also understand the delay, how we are going to find out the delay, that also we will see. And for any gate, it is measured between 50% of input transition to the corresponding 50% of the output transition, clear. So, we have to take 50% from the input and to the input to the output, clear. This is the time required for a signal to propagate through a gate or net, that is also called a wire or interconnect, clear. Means how much time it is taking to transfer the information from source to destination, that we have seen, clear. So, the overall propagation delay can be measured by taking the average of the delay from high to low or from the low to high switching. So, overall if you want to find out the propagation delay, you can take the average of these two and you can find out. So, from here if you are taking a 50-50% from this input diagram and output diagram, you can easily understood. This is my input. Okay. So, this is my practical case and this state 1 is my ideal case. So, we are not taking the ideal case, we will see the practical case. Okay. So, if we plot a 50% line over here, the 50% voltage, suppose if it is a 1.8 volt, maximum is 1.8 volt, then 50% is 0.9 volt. Clear. So, based on that you can see initially we are having a 0 input, for 0 input we are having a high output, and as this is the slope, this is the rising slope. So, this is called rising time. Clear. Once it is logic 1, the output will be slowly discharged. Okay. Then again it is a logic 1. Clear. So, if we take a 50% from here, we have to draw a vertical line over here. Clear. And again here from 50%. So, we have to check this cross point, this point and this point, the distance between this, you can take this point as a T0 and the next time is T1, similarly here T2 and T3. Clear. So, we have to check from propagation delay from high to low. Clear. The propagation delay from high to low is T1 minus T1, T1 minus T0, the difference between this T1 and T0. Similarly, low to high, this one it is T3 minus T2. Clear. So, if we take the time difference of these two and if we take the average of this one, we can calculate the propagation delay. Clear. Similarly, the rise time and fall time. What is rise time? So, the rise time is defined as the time required for the output voltage to rise from the 10% level to the 90% level. Okay. That we can see in the previous slide, this one. So, suppose this one is my 10% and this one is my 90%. Clear. Similarly, the fall time is like we are having a waveform, this one is rise and this one is fall. So, this is called T rise and this is called T fall. Clear. This is a fall time. So, that also we can evaluate with by using this formula. So, this is the how we can see the 10% voltage and the 90% of voltage. Clear. Now, if we take a horizontal and vertical line between these, clear, if we are having input on top of it, then the difference between these two we can take as a rise and the fall. Clear. So, this one is a rising edge for the output and this one is a falling edge for the output. Okay. So, the difference, and if you take the average, you can take the overall propagation delay. Clear. Thank you.